Hello, good evening to everybody. Welcome to a live session of Point-Set-Topology Part 2 course. This is the second live session. You must be already having almost some 22, 23 lectures. So there may be quite a few questions. The interactive session, as usual, is meant for you to come up with queries and I try to explain them more on the spot. That's what it is. Uh, Unfortunately, last time, the first live interaction session, nobody asked any questions. This time, if it's better if you ask some questions, even otherwise, I have a little bit something that I would like to tell on my own, namely, one of the questions asked in the forum, which has not been answered, I would like to answer part of it. So up to you, please start asking your questions. So far, nobody has asked any questions. Before proceeding with the discussion from one of the questions in the forum, I would like to know whether any TAs have joined this session. So TAs, any of them are there? Okay, Sushil Singla is there. That's good. Anybody else? Well, the question was, I suppose, like that. Any new universe on mapping of the real life to the space 301. This is a very good question. Again, I would like to know whether the person who has asked this question is in the live session. He or she has to just say yes or no. That's all. No, there won't be. So I will wait for a minute whether the person is there or not. So it looks like even the person is not there, or there is some problem with communication. So let me proceed with trying to answer this question. Right on the outset, I want to say that I don't have a complete solution of this problem. whether I can answer this question or not. Riptayan Santra. Riptayan Santra, okay. I am going to handle that case also in the discussion, but n equal to 1 is one single case. Even there, I don't know the answer. So that is good enough to tell you the story here. So listen carefully. We have some material in this course on dimension theory. If this question is taken up after you learn this dimension theory, it will make better sense. Even then, there will not be a complete solution right now. I don't have. So let me try to analyze this question. R is something like a one-dimensional space. R2 is what is called as two-dimensional space. R3, R4, etc. They are all Rn. Each Rn is n-dimensional space. The topological theory of dimension tells you that different dimensional spaces cannot be homeomorphic to each other. Even any non-empty subsets in one of them cannot be homeomorphic to another one. So this you can say is a consequence of what is called as invariance of domain. So I have used certain words here which I would not like to define because these things are done appropriately later in this course. Point is, you know that instead of C01, you can simply ask the following question, namely whether there is any continuous open mapping from the real line to R2. Even this I cannot answer. You understand that one? Real line to R2. Now, instead of C01, why I have taken R2? C01 is a Banach space. Banach spaces have been introduced to you already. It is actually a separable Banach space. The set of polynomials defined on 01, polynomial functions, they will form a Banach space basis, not a vector space basis. Okay, namely, if you take the subspace generated by all polynomials and then take the closure, that will be C01. This is precisely Weierstrass approximation theorem, which is also done in this course. So C01 is separable, but it's infinite dimensional space. Whereas all Rn, they are Banach spaces. Actually, they are all Hilbert spaces, but I don't want to bring in the Hilbert space thing here, which we are not discussing. Okay, all Rns are Banach spaces of different dimension, n. And C01 is infinite dimensional. As a vector space is uncountable dimension. As a Banach space, there's a countable base such that closure is the whole space. Okay. What happens is, if you want to reverse the arrows here from instead of Rn to R1, then it is very easy. There are always the projection maps. If you write Rn, members of Rn as x1, x2, xn, just take any one of the coordinate function, that will be a continuous open mapping, which is also surjective. to R. You can take Rn and Rm, m less than n. They are all open quotients. So more generally, the same question could have been asked for Rn to Rm, where n is less than m. Is there a continuous open mapping? Now, if you drop out continuity, then this is true. You know, R2, just take the real line, just take a closed interval. You can have continuous functions which fill up R2, R3, R4, and so on, not whole of R2, R2, R3, but unit queues, okay, inside that. So there are functions from R to R2 which are continuous and surjective. R2 to R3, R to R4, everything. You can have continuous rejection. Those mappings, not only they are not open, they are not open, okay? I'm saying precisely, it's no question. You can show that the whatever you have constructed, what are called as Peano's curves and so on, space filling curves, they are not open mappings. Not only that, they are not even injective. Now I am bringing you another concept here, namely continuous injections, and forget about the open mapping. Then I know the answer. Namely, there is no continuous injective open mapping or continuous injective surjective mapping. One hand on two maps. Okay, from R to R2, R to R3, and so on. Even that one can know because of dimension theory. Okay, injectivity, one and on to map. Injective map you take and then take the image. That image will not be an open subset. So injective mappings, which are open mappings, are not possible. You don't have to worry about subjectivity. You can take just the image. That image will not be an open set. So the original function cannot be an open mapping. All this is not very difficult to see, at least once you know the dimension theory. Without that, nothing is easy here. Okay. Nevertheless, this question is very good, but the only thing is now you have to search for examples. Examples which will prove that there are something like, what is the meaning of examples? Can you have open mappings at all open mappings which are quotients? Okay, if you take n less than m, there are no open quotients, is what I want to say. That has to be a proof, not just example. But R into Rm, there are plenty of them. But now you can ask just open quotients mappings. You look for all of them, try to have examples, and then see that you are not getting. That means you like to prove a theorem. So when you want to say something, prove something, and you are not able to, then you try to construct an example. That's all. Not that you will succeed. Okay, so that is the idea. Okay, so if you give an example, if you succeed in an example, well, you have settled the problem also. Then also. Okay, so my gut feeling is that the answer is in the negative, and so you have to prove that there is no such. Okay, so there is a very nice input here now. I am very happy that Gupta and Santra has put something input, but he says that uh, C01 is locally compact. We know that C01 is not locally compact. Okay. This fact is also proved in the course. Uh, if you have, if you have compact, locally compact topological vector spaces, then they have to be finite dimensional. Okay, one knows the C01 is not locally compact, first of all. After that, what he says is there is no continuous mapping from Rn to C01. That is wrong. What you have to say is no continuous function which is open. Okay, open. So for that, you have to show why the local compactness of C01 gives you a contradiction. Okay, so that I think is possible to prove. If that is correct, then you have solved this problem. Okay, so again, Santraji, there are all sorts of subspaces. Rn itself is a subspace of all Rns are subspace of C01. You can take any uh, finitely many independent vectors, say x1, x2, xn inside C01, f1, f2, fn, polynomials or whatever, and then take the linear span of that. That will be homeomorphic to Rn, a copy of Rn. So there are plenty of them. So that is not the problem. The problem is, go back to your original question. Suppose you have a map from R or Rn to Rn, which is open and continuous. That's all you want. Okay. So since the mapping is open, the image is an open subset. Therefore, by shifting the origin, you can actually say that origin is also in the image. Okay, without loss of generality, you can assume that the origin itself is in the image, and the image is an open subset. Okay. Now, to begin with, the Rn, if you take the, say, origin goes, some point goes there, you can shift the origin in the Rn also. 0 goes to 0, just for the sake of clarity. You can assume 0 goes to 0. And then a neighborhood of 0, you can take a disk which closure is compact, right? Under any continuous function, the image of that set will be compact. The interior is an open set. Okay, the interior has to go inside the image of this compact set, right? Interior is an open set. If you assume F is open map, interior will be an open map. Interior will be an open subset. So that open subset is contained in the compact set, right? Therefore, the closure of that open set will be also compact. So you would have found the neighborhood of the origin, okay, which has compact closure, which means a compact neighborhood, and that is not possible in C01. So this will actually, by just asking a good question, maybe some with small mistakes, you have solved this problem. You have solved this problem. There are no open continuous functions from Rn to C01, just using local compactness. That C01 is not locally compact. Do you understand this one now? No, dear. You say it is solved for only surjective case. I don't assume surjective case. You see, I repeat, take any open mapping. Okay. Any mapping, the image has to be non-empty. An open mapping, the image has to be open. Okay. Now, if you use the translation in C01, they are all homeomorphisms. So if you compose with the translation in C01, that will be still an open continuous mapping. By using a translation, you can assume that the origin is there. That part is not necessary at all. For any point you could have done that. Okay. Even if any point in the space C01 has a compact neighborhood, that would be contradiction. Okay. So no subjectivity is assumed here in this argument. Any more comments? Or this is satisfactory, you can go to some other questions. Wonderful. So that's the one question I would have asked you. One thing is very clear. Now we have local compactness. If you throw away that one, then there is no way, you don't have anything. So you have to think again afresh. But if you bring in continuity, along with continuity, whenever you are talking about Banach spaces, you would like to bring linearity. Then this question will be very easy to understand and also tractable in the function analysis course. Okay. You have to use tools of function analysis. For example, all separable Banach spaces, all separable Hilbert spaces are isomorphic to each other. Okay, they are all isomorphic to C01. So there will be an isomorphism will be automatically a continuous open mapping. Okay. So you can use open mapping theorems, closed graph theorems, and so on to solve this problem. Without linearity, it is again in the domain of topology. Okay. Then it will be again a hard problem. Okay, non-locally compact, both of them infinite dimensional, whether there will be a continuous open mapping from one to the other. Anybody wants to add any more comments or ask questions? If there are no questions or comments, we would like to close this session. Okay, so wishing you all happy learning of this course. There will be one more live session, maybe after another 2 weeks. I just want to tell you that if you need more live session, you have to be live. You have to ask questions. Okay. And if you want more live sessions, you can demand it in the forum. There is a feedback form. You fill up that one, then we will know what goes, what has to be done to enhance the benefits of this course. Thank you. We'll see you next time.